We're nearly there. Sometimes it's the hardest thing about class, watching that clock tick upwards. Okay, it's official. Looks like we can start. Welcome back, everyone. We're on Tuesday, so we're about to be midway through the entire first week. Before you know it, these weeks are going to feel like they're flying at some points. So it's good to appreciate where we're at while we're there. For week one, the announcements are there's been a major revision on the differentiation rules document. So if you printed this out or prior downloaded it, the corrections there. The quotient rule was severely damaged. There's a negative sign in the numerator, not a positive sign. I can't believe that slipped my proofreading. So sorry for that error there. That's a good thing to keep in mind of. Product rule, put in a plus. With quotient rule, throw in that negative. Aside from that, there's been a lot of requests about other review material, particularly Chapter 5, Fundamental Theorem of Calculus, Substitution Rule being major ones. So I placed them here as well, and as well as hyperbolic functions. If you had a class that went kind of fast through them or even skipped them altogether, their definitions are here, just sketched down on the margin. But the full definitions of all the hyperbolic functions, working with their derivatives, are all posted there as well. Well, that's our pretty much the whole set of announcements for today. We won't spend like a half an hour introducing the class each time. But like we mentioned at the start of class, will just be a fast roundup of announcements. We'll always know about where we're to jump into. And then I just turn it over before we start to see if there are any questions among the class. So any questions at all, folks, before we get started today? Okay, well, we got through the major topics in section 7.1, but we actually haven't even touched on integration by parts. We were just looking at some review material to start connecting with Calculus 1, what we're about to do in this course. The due date's September 3rd. So what that means as far as the calendar is, my intention is to complete those notes sometime on Thursday, and I give a week away for the due dates in this class. That gives you sufficient time to work on the problems, ask questions, get them answered to complete the assignment. So let's jump in where we left off. We're on example 3, but before example 3, here's the entire theorem for integration by parts. So here's the idea. In integration by parts, we have two functions we're considering, f of x function, which we denote by u, a g of x function, which we denote by v. And then here's the whole theorem. Well, let's work through the other parts. They're differentiable on a common domain, the open interval from a to b. If their derivatives are also further continuous on that same open interval from a to b, then that's integration by parts, the entire theorem. It's kind of mysterious when you take a look into it. So what we'll be doing with this one is give a full derivation of the theorem. And we're not going to do loads of derivations in this class, but we will do a derivation when it's kind of short and sweet. It's not going to take 40 minutes, 50 minutes of class time. When it emphasizes skills we're going to use on the next problem, reinforces or review prior skills that we've seen before, and this derivation hits all those sweet spots. So when it makes really good sense for the course to explain what's going on, the derivation is sometimes the best explanation. So here's how we would do this kind of derivation. We start with the two major moving parts, the functions. Let's write it out as u equals f of x. And on this table, this looks really weird. Go down one, right one, v equals g of x. That table looks a little bit weird, but this is how we're going to solve the problems. So in this weird format here, in column 1, where the u function is, u equals f of x, we immediately calculate its differential. Differential, just for the fast review once again, means if it's u, down below we'll put in du. If the function's f of x, we'll differentiate it, call it f prime of x. If the variable is x as an independent variable, we'll slap on a dx as well. So on the first column, we go du equals f prime at x dx. Now on this column, again, it looks a little bit weird, but when we're solving a problem, we write down row 1, and we actually don't always have v. We have to determine what v is. But we can double check our answer, because whatever goes here, we take the differential again and place it upwards. So above, it's going to be dv equals g prime at x dx. So we know where the u and v comes from, but again, it's all over the place on this formula. It's kind of a strange one. We're going to be practicing it a lot in these notes, and integration by parts doesn't just go away. It can enter in problems in section 7.2, 7.3, and so on. So with those down, all we have done is put down a u function, it's differential, a v function for g of x, it's differential above. But here's the next main idea, what's really going on with integration by parts. On the next line, let's put down f of x times g of x. Differentiate that whole result. We'd be using the product rule to form that derivative here. And this is really where integration by parts is coming from. It's a careful rearrangement of the product rule is what we're getting when we go up here. So let's do that product rule. I'll differentiate f first to get f prime at x. Copy g of x plus, then go f of x copied, multiply by g prime of x. And that's the whole entire product rule. Now, this is a bona fide equation, so whatever you do to the left-hand side, you are allowed to do the same exact operation on the right-hand side. What we mean by operation is pretty broad. You can find the antiderivative, use this symbol, integrate both sides as an antiderivative all at once. So the antiderivative of the left-hand side would look like this. We now take the antiderivative of the entire right-hand side. Properties of integrals say the integral sign as a definite and indefinite integral can partition across, or distribute across is a better way to say it, an addition sign. So we can integrate f prime at x, g of x, dx, plus separately find the antiderivative, the indefinite integral of f of x times g prime of x dx. So it starts off as a mysterious table of differentials. We run through a product rule, and now we just essentially integrated all three terms on both sides of those equations. Any questions whatsoever to this stage? Okay, one of these we can solve right away. It's going to be from when we did this problem down here. Recall when we were solving, let me place it maybe up here, the antiderivative of x times sine x prime. Well, that's just like the antiderivative of f of x times g of x prime. The answer to that antiderivative was just x sine x at a constant. We're going to not put down that constant c this time, because in integration by parts, the tradition is to put down the constant of integration once you solve this last integral here. So we'll leave that constant off and just write in the integral sign here and the differentiation operator here cancel, and you just get f of x times g of x on the left-hand side. So here's f of x, g of x, and let me recopy these. Well, f prime at x times g of x dx, we could rewrite that as g of x times f prime of x dx plus, I like the ordering here, I want the derivative next to the dx, so f of x times g prime at x dx. And again, it does look like a kind of mess, but that's where the function indicated by u, f of x, the function indicated by v, g of x, start to come into play. F of x is here and here, where we see the f prime at x dx. G of x enters here and here. It's also, there's a g of x there and an f of x there. But notice where you see f prime of x dx, you go up to this table here, That's just another way to say du. So this whole piece is du. Likewise, where you see the g prime at x dx, there's an abbreviation for that through this equation. Through the inequality, we can just call g prime at x dx a dv. So differentials are kind of weird. They enter in all over the place, calculus 1 through 3, vector calculus. And this is one of the weird uses of them in stating an integration by parts formula. So now let's rewrite all this. F of x is u. G of x is v, so here's uv. It's equal to the integral of g of x is v, times du, or we would just really say v du is the better way to indicate that, plus f of x here is just the u function dv, so u dv. And at this stage, right where it stands, that's just as good as a formula right here as this one is. But it's been rearranged. The official integration by parts formula has subtracted an integral from both sides. The one they subtracted is the v du integral. Subtract that from both sides, solve for u dv. Here's u dv. And that's integration by parts. So watch where this integral is, u dv. The integral of u dv would be equal to, subtract that one from both sides, it will be uv minus the integral of v du. And so that's the final entire statement of integration by parts. Everything just kind of gets rearranged. You take the product rule, integrate both sides using an indefinite integral, solve for the u dv integral, and that's the entire formula in a nutshell. Its purpose is to solve for functions or solve for antiderivatives where there's a product in the integrand that we can't simplify, that we can't unwind, we can't use substitution our way out of in any kind of way. So this is the derivation, uses our good work here on differentials. This table we copied here, we reproduce when we go to solve a problem. And any last questions at all, folks? Just tracking through the derivation itself. Okay, so one idea about this is you can think of u substitution as a literal unwinding of the chain rule. And the analogy here is less perfect, but in a certain sense, integration by parts is unwinding a product rule. That's not a perfect analogy because, again, we moved the equation around. We rearranged it in a certain kind of way. So let's apply this. It's one thing to derive it, and it's a whole nother thing to use it in practice. And example 3, part A, is us using it in practice. We want the antiderivative of x times the hyperbolic sine x. And none of our tools of the trade are going to help us with solving this one. So what we'll do is break it down this way, which means we're fundamentally just writing down a table that goes like this. We need to pick a function for u. Something is going to go there. And then once we pick the function for u, everything else is going to be dv. So that's row 1 from the derivation. It goes u dv. Below we'll differentiate u. Below we'll find the antiderivative of whatever we have on this equation right here, the differential. It all now comes down to, how do you pick u? If you can pick u correctly in a way that gives us forward progress, everything else is dv. So the process hinges on, what should u be? There is no one formula for this. It's just like u substitution. There's not a formula for telling you exactly how u substitution will go in every single situation. Functions are extremely vast, but there are some guiding principles. So for integration by parts, this is the acronym for that major guiding principle. Let me space this out a little bit more. LIATE, I don't know exactly how you would pronounce it. Liat, I guess, would be a way to say it, is a way to pick what your U should represent. This is not guaranteed to work, but you'd have to work extra hard to find a problem where this method as an acronym fails to work. So I think that would be a problem that would be a bit extreme, not a fair one for an exam, probably not even the homework. So if you like acronyms that help as a guiding principle, here's how it goes. L stands for logs. Let me just write it down below. L is standing for logarithms. So what that saying is, if there's a natural log in the problem, automatically that should be your U. That's a really good starting point. The moment a natural log, a log base 7, anything like that occurs, pick that as your U. You're probably going to be in great shape. On the next level is I. I stands for inverse functions. That one probably deserves some examples. When we mean by inverse functions, we mean functions with the inverse symbol explicitly indicated in its notation. So for examples, something like maybe tangent inverse or sine inverse. If an inverse function in that kind of form ever comes up, then really good use for your U in the U substitution. After that, A stands for just algebraic. What we mean by that, for examples, is maybe something along the lines of maybe it's just literally an X. Hey, like in our case, there's an X. That's the algebraic part and the LIATE acronym method. That means if X occurs, that's probably the best choice for you in integration by parts. If it's maybe X squared plus 3x plus 4, that's a more built up algebraic form, same kind of idea. Then down the line, you can probably guess what T stands for. T is just going to be trigonometric. Trigonometric like sine, cosine, even the hyperbolics like hyperbolic cosine, hyperbolic secant, and so on. The trigonometric function comes up, but there's no algebraic, there's no inverse, there's no logarithms, then pick your U to be that trigonometric function, is what this method is saying. So we read it left to right, and finally for E, exponential, let me keep the format the same. Got to put T for trigonometric, A algebraic, sorry, I forgot what my formatting was. E stands for exponential. So examples on that one could be, say, e to the x, 7 to the negative 4x. So even those kind of exponential functions would be good choices for your U in U substitution. So this mnemonic gives us a good method for picking what U should be, depending what's going on in the integrand. So we'll work through this using this mnemonic on the problems down below. Here's the entire formula for integration by parts. And maybe one other guiding principle is, sometimes you can pick a U where when you go to take the differential, the complexity doesn't change. Maybe it comes more complicated. For example, if I picked U as hyperbolic sine, the differential would be du equals hyperbolic cosine times dx. It's just as complicated as a hyperbolic sine. No reduction in complexity, which is what we want to see. We're trying to make the original integral more simple. But if you switch over and say, don't pick U to be hyperbolic sine, pick U to be x. Then when you go to take the differential, there's a major reduction in complexity. The derivative of x is just a 1. So we would say du equals 1 times dx, or even just dx for short. So we should see a reduction in complexity. If it becomes simpler in that kind of way, It's not guaranteed to work, but you're probably on the right track. So we do this just as the derivation. We pick one portion of the integrand. Here it's the function x. But then here's where it gets a little bit different. We're running through row 1 first. If you pick u as x, then absolutely everything else, including the dx, that's all dv. So dv becomes sine hx dx. So now we have to solve this part of the table going backwards. We have to say, what was the function v whose differential became dv sine hx, or rather dv equals sine hx dx? But really, when you're going in this direction, this is all you're doing. You're finding the antiderivative, and not a generic one with the arbitrary constant c. We pick the simplest antiderivative possible. The constant c is set to 0. So we just find the simplest antiderivative. So what's the derivative of sine hx? Our antiderivative? Well, through our handy formula as a review, if you differentiate hyperbolic cosine, you do get sine hx. So going backwards is finding the antiderivative, and that tells us v is hyperbolic cosine, or you can just say cosh x is a decent way to verbally say that. It's a good idea to double check, just like with any antiderivative you form. You can double check you have the right function here by forming the differential and seeing if this line's correct. So the differential of v equals hyperbolic cosine would be dv. Derivative of hyperbolic cosine is amazing. It's positive hyperbolic sine, not negative. So we're on the right track. And then just hit it with the dx to form the complete differential. So this is the side work, the preliminary work to even just start off integration by parts. But a lot of ways, it's not all that terribly different than, say, u substitution. In a u substitution, the side work is picking your u, forming a differential, rearranging it if necessary, and then substituting in the information. Our difference is there are two differentials. We pick a u, a dv, and then when we go over here, we're not substituting everything back. We're using that part of the formula right up here. So it's not a bad idea to just write down on paper what the formula is. The formula goes integral of u dv equals uv minus the integral of v du. We already know what u is. That's the wrong color. Let me fix that. We already know what u is. We selected it to be x. So this x goes to that x. We already know what dv is. We selected it to be hyperbolic sine x dx through that row, this table, that entry rather. Writing this down is really pretty helpful because it helps us just do all the connections right here. There's 4 pieces to plug in. Any questions before we start plugging in the information on the uv minus integral v du? Okay, well, if you're a fan of color coding, this is pretty much all it is. Put in whatever you said u was, whatever you solved v to be. Also put v here, put in du here, and you're subtracting these quantities. So in the next line, it's just a whole bunch of substitutions. For u, we're throwing in x times v is cosh x. So that's the first level of substitutions. Minus the integral of v cosh x. So that's the v part. We also throw in du, and this is kind of the moment of truth. If this function here didn't reduce in complexity, if it was something more involved, then this integral is still hard. It might be harder even if we picked u wrong. If this simplified quite a bit, making that integral not hard to solve, we're on our way. Our work is just about done. And that means we're in a good shape. 1 times dx, we can just write in as literally dx. And that's what du is boiled down to. All we now need to do to simplify, to solve this entirely, is find the antiderivative of hyperbolic cosine. That's just hyperbolic sine, citing our differentiation rules here. Going backwards from hyperbolic cosine gives us a hyperbolic sine. There's some signs we have to track with that negative in the middle. So in the end, this all becomes x cosine hx minus sine hx. This is an indefinite integral, so we throw in our arbitrary constant of integration, c. And we've done it, folks. This is one of those integrals that is completely 100% avoided in a calculus 1 setting, unless it somehow could reduce in a certain sense, because this one involves the product rule in some indirect type of way. When we check our answer, we're just differentiating this, but notice right there, when you check your answer, product rule does in fact come up. So it's in that kind of sense, we're unwinding a product rule with a little bit more involved. So when things are being multiplied in this way, to get the antiderivative is suddenly a lot more convoluted. If it was just x plus hyperbolic sine x, we're on our way. Let's put that down on paper just as a comment. The reason we had to work so hard is because it wasn't this integral. X plus sine hx, that's just the sum rule for antiderivatives. It would have been x squared over 2 plus hyperbolic cosine x plus a constant, and then we're just totally done. We can integrate term by term if things are being added and subtracted. We can use u substitution if there's a function composition, potentially. But when things are multiplied, it's now kind of a little bit of a fight. We have to work hard. We have to come up with these pieces of information here for the side work and hope that this integral is solvable. If it's not, we just try something else. There's a little bit of trial and error sometimes in getting through these. So for the rest of these notes, we're going to practice more indefinite integrals. And at the very end, we'll do some of them as definite integrals just to get that needed practice. You'll be practicing some as well in the homework. If you get stuck on any of them, don't hesitate to ask about them. Office hours, before class, after class, I'll be happy to help out. Even just an email, I'll be very responsive and always happy to give hints on emails if you get stuck on any of these questions. So let me copy this down, and now we're on to the next one. I guess we probably should not try to cram it in here. Let's go to a whole new page for the next example. Here's our part B, w squared e to the power negative 2w. We were just looking at this, so here it is again for easier reference. So in looking at how to start this one off, let's begin by writing down our handy table. We need a u function. Acronym down below here helps us pick u. After we get our u, everything else in the integrand will be dv. We'll find the antiderivative, that's going to be the v. We'll do the differential in the left column, that'll be the du. And so this is how integration by parts really starts out. Solving these components, and then running through this part of the formula here. Now looking at this, it's weird with a variable w, but that's just a distraction really. It can be any variable. E to the power negative 2w is the exponential function, but a for algebraic has higher precedence. That's a power function. It's a quadratic, you could say as well. That's what we mean by algebraic. So the w squared is the a portion, which strongly suggests that's a good place to start off trying for u. We could let u be w squared. We do need the differential. That's part of the process on running through this whole formula. Notice that du is up here. So we need to compute du, the differential. We take the derivative of w squared, 2w, and then we multiply it by dw as well. Don't forget these pieces right here. It's easy to leave them off. If you notice I ever do that, don't hesitate to call it out. A full differential must have the du, it must have the dw. Well, we picked w squared to start out. That's nice because that means everything else, including dw, fills out the dv column. So really, this is the pivotal entry right here. Once you pick u, everything else flows, and now it's just up to, can we form and solve that last integral in a reasonable way? So for dv, throw down e to the power negative 2w dw. Now next, we need an antiderivative. And getting these antiderivatives, like we mentioned before in the notes, it could be a little bit of fighting, but if you find a special kind of antiderivative that looks like something along these lines, sine 3x, for example, the input to that exponential is a linear function in the variable w. That means you really don't actually have to use u substitution. Thank goodness, because that would make the whole work start to explode if you used u substitution in every single scenario. So if there was a 3 right here, we just had to divide by the 3. The negative is part of the antiderivative, and we solved for the antiderivative. Same idea on this one. If you want an antiderivative of a base e exponential, you can start off by saying, let me add a little bit more space first. You can start off by saying, add a little space and then the base e exponential. If the input is negative 2w, just take that negative 2 and divide by it. So that's matching these steps that we took right here, where we didn't do u substitution on this one at all. We just noticed it's pretty close to a sine x. If it's linear, degree 1, divide by that coefficient on x. Coefficient happened to be negative, so we divided by negative 2. I just formatted it in that kind of way. Next other interesting thing is we don't add on the constant. We want the simplest antiderivative, so we stop right there. And u substitution can sometimes get us mixed around. For example, when we did that differential, we moved that 2 over to the left-hand side because 2 wasn't in the integrand. But we never do that here. If there's a 2 in that spot, it's got to stay in that spot. So integration by parts is really a whole new kind of way to operate. Don't rearrange this differential whatsoever in integration by parts. You know, that's a decent thing to add into the notes just right here. We do not divide by this 2. In integration by parts, it's got to stay exactly where it is, or we'll be off in our answer. Okay, so problems in Calculus 2, just like a decent amount of problems in Calculus 1, they do get a little bit long, and this one has a good amount of analysis just to get started. But any thoughts or questions on the startup for this one? Okay, well, next thing we should do is, here's the formula. Instead of writing down the whole entire formula, you could notate this by saying, this is your u, this is your dv, and the whole thing is going to be equal to uv minus the integral of v du. That's how I would typically write it down personally. And even though I have the formula memorized, sometimes I still just write this down because when lots of things are being substituted in, it just helps your eyes for the sake of accuracy to see what is going where. So instead of color coding it, here's another way to help your eyes to show what goes where. It's a kind of game that you play on this table. You take the main diagonal and just multiply them together. You're taking u times v, so whatever is here for u, whatever is here for v, just multiply them together, and that's the first portion, uv. So it'll be w squared times negative 1/2 e to the power negative 2w. Usually I'd put that -1/2 way out in front, but I just wanted to show where all the moving pieces are going instead of rearranging anything on this one. So there's the UV portion. Then we go minus the integral of, well, instead of color coding this one, here's another option. When you're doing the integral of v du, the next thing you're doing is just taking this and this and multiplying them together. You're just multiplying the bottom rows. So it flows like this. Multiply the main diagonal, multiply the bottom rows. Main diagonal is this part, bottom rows is this part here. So v is -1/2 e to the power of -2w. And then the du part is this, 2w. Notice that 2 really has to stay there. 2w dw. So, but if you're a fan of color coding, here it is as a color-coded object. So that's putting it all together to this line right here. We still have to solve this integral, but you know what? It's still kind of nasty. The complexity did go down. That was degree 2 for w squared. Now it's degree 1, w times the exponential. If the degree keeps on dropping, we're on our way to finishing this one. So even though I can't give a direct answer immediately right here, like we could on this version, antiderivative of hyperbolic cosine, we have made legitimate progress. So we just keep on going. Sometimes in U substitution, you can do U substitution multiple times in the same problem. And likewise for integration by parts, it can be sometimes done multiple times on the same problem. I wouldn't throw a problem at you on the homework where this is like degree 5 on W, and you have to use integration by parts 5 times. Whenever that happens, you change the formatting and use a different kind of scheme just to simplify it. But I'm going to stay away from those kind of problems in the homework and on exams. U sub integration by parts is only going to have 2 levels at the deepest for the purpose of a decent exam problem and homework question. Beyond that, it's just more kind of tedium in my opinion. So let's simplify this a little bit further down. I think this portion, this first term, is better written as -1/2 w squared e power -2w. The 2's here, 2 times a half cancel. This -1 can cancel with a negative on the outside, so we can cancel our negative signs. We're taking the antiderivative of then just w e to the power of -2w dw all together. So if we can solve that integral right where the red dot is, we're on our way, the problem is over. But it's integration by parts again, so we just go ahead and we use it again. So depending on how mindful you are trying to be with abusing notation on variables, worrying about scope, the way I typically think about these problems is if I'm about to use integration by parts again, my u and v here, I consider them to be new variables. The scope of the variable u and v is only for this first part. I'm going to use another u, another v here, but these are in a completely different kind of scope. Or we could use different letters of the alphabet if you like, or maybe subscripts, u1, v1 down below here so they don't conflict. But this is a decent strategy. Think of u and v as being a completely new set of variables in a new kind of scope. The scope is just for solving that new antiderivative here. So still we have something algebraic for w. U should then be w. That informs us everything else should be dv. So dv is e to the power -2w dw. The good news about using integration by parts twice is if you ran through it once, the second run through is usually a whole lot faster. So we picked u in the same kind of way. W just has degree 1 this time. The differential, you can call it du equals 1 for the derivative of w times dw, or it's often just simplified like this. 1 times dw algebraically is just dw. dw obeys the same kind of rules as algebra, so we can just simplify it if you prefer. And if you found the antiderivative once for the dv here, let me erase these arrows so the visual noise goes down. You found the antiderivative once, you don't have to reinvent the wheel, just reuse that answer. V is still negative 1/2 e to the power negative 2w. So we're going over here and just reusing the uv minus integral v du formula. Let's scroll down a ways. So let me copy what we have, negative 1/2 w squared e power negative 2w. We've got that down pat. Now here's the formula once again, minus uv. And hang on, that's not a minus, that's a plus right there. Copy plus to plus, sorry about that. Formula for this piece is uv minus the integral of v du. So same formula that we cited up above here. So u and du will be substituted in the same way, as will the v's. Now the problem is just about there. So let's copy in negative 1/2 w squared e power negative 2w plus. Next substitution, we're taking this u times this v, so that's going to be, whoa, wrong pen, let me try again. W times negative 1/2 e to the power negative 2w. So there's u and v minus the integral of v once again. So here's negative 1/2 e to the power negative 2w. And now this part right here, du, is just dw. So now the complexity on this integral is highly, highly reduced. If we can just get the antiderivative of this e negative 2w, our work is done. The constant negative 1/2, we can just export it out to the front of the integral sign. It'll become positive 1/2 altogether. So we're just focusing on the antiderivative of that piece alone. But notice this becomes kind of a negative sign hell already, right? There's two negative signs here. When you do the antiderivative here, you get a third negative sign. And so you want to really carefully track those out. I'm writing it down this way in the notes just because I want to show how everything substitutes in back into the problem. But if I was writing it down on paper personally, I probably would have put this as a plus 1/2 to the left here, just so I can consolidate things out, not get mixed up on the negative signs. But the way it stands, we can still achieve this. Let's rewrite our answer as negative 1/2 w squared e power negative 2w. This simplifies as negative 1/2 w e to the power negative 2w. And those two negative signs cancel for a positive 1/2. Antiderivative of e negative 2w. We did it for the second time here. Now we're doing it for the third time. You just multiply by another negative 1/2. So this would become negative 1/4 e to the power negative 2w plus a constant. Let me pause on that negative sign. Does that make sense to folks on it being negative, being a negative 1/4 altogether? Just for the sake of clarity, especially if you come back on the notes, the way I visualized it was that whole piece is really 1/2 as a positive out front, e power negative 2w, dw. And when we solved that antiderivative, we had to multiply by negative 1/2 again, times that, gave us the negative 1/4 altogether. But again, you have to carefully track those negative signs. They can get kind of unruly in the end. So that's our total answer. You don't have to do anything fancy to this. You don't have to find the least common denominator, factor it at all. If you leave it in just that format, I'm pretty happy with it. Some people have a strong urge to factor out e negative 2w, but that's going to be completely your call. So that was a long problem. This took the entire page. I don't know how w got in there. Let me see if I can get it out. There we go. Any questions or comments with the whole process on this one? Okay, well, integration by parts is a fundamental technique whenever we can't simplify that down in some way. So it's one function, or maybe a sum of functions like x plus hyperbolic sine. That's a wonderful problem to solve because you can go term by term across addition or subtraction. But major problems in integration when functions are multiplied, those are the tricky ones to unwind. Here's the weird thing about integration by parts. If you've done the reading in this section already, you'll find that this technique is actually really, really versatile. It's not only in the case functions are multiplied that it works, it also works for this one. Antiderivative of cosine inverse on its own is an integration by parts problem, and that's a really surprising statement because it really doesn't look like it to me. Doesn't seem to fit the spirit of the process, but it is. Integration by parts is the only way I know how to get to the antiderivative of cosine inverse. You'll notice we kept completely away from these kind of problems in the Calculus 1 setting, but that's because we didn't have the powerful tools that's going to give us the antiderivative. So let's see how this one goes. The reading in the textbook, I think, does tangent inverse, so you might have seen a similar problem already. The feature or the mnemonic here, LIATE, is relevant. We're on this level. I for inverse function. An inverse function comes up, it strongly suggests that should be your U. So even though it's kind of a weird problem, if you know you're using integration by parts, this mnemonic helps out tremendously. Let's let U be cosine inverse of x. Then that's like the whole thing. Well, not exactly. It's the whole integrand, but it's not everything in the integral because there's still a dx left over, and that's what dv is supposed to be, everything else. And the everything else on this one is dx, that's all. So that's how an inverse function like this will enter into these kind of problems. And to be honest, if this kind of technique comes up, it's really going to be cosine inverse, sine inverse, tangent inverse, or any of the reciprocal function inverses. That would be the most likely setting that this kind of problem would come up. So for inverse trig functions, this is how we would go at it. This is still not easy to solve because we have to dig deep in a certain sense, right? This time, the rightmost column is not so bad. You integrate both sides. That will give you v equals just x. We double check by taking the differential. V goes to dv. Derivative of x is a 1. There's really a 1 there through algebra properties. And then you multiply it by dx. So if you have dv equals dx, it just rewinds into v equals x each time. But this is where review on Calculus 1 is really, really necessary. The differential of a cosine inverse, the way I memorize this is, if it's a cofunction, I'm expecting a negative sign. And sine inverse, cosine inverse, they both start with the square root. And they go with a variable squared minus 1, throw on a dx. So these are the kind of formulas that we have to be ready to go with. I think these inverse trig functions, when we differentiate them, they're tricky to memorize. So if you feel like you need kind of a safety net, if it feels a little sketchy, this is information you can put on your exam 1 formula sheet. Go to the Canvas webpage, differentiation rules, where it's been revised. And down below here is the inverse trigonometric functions. Lots of great strategies for memorizing them. Notice that there's really just 3 sets of formulas you're memorizing, and they differ by a constant multiple of -1. So similarly, sine inverse, cosine inverse are just about the same, but a cofunction implies a negative sign in the derivative formulas for every one of the cofunctions. So with that all down, we just slap it with that formula, substitute in, and hope that our last integral is achievable. Yeah, go ahead.
On the sheet, it says that it's 1 minus x squared, not x squared minus 1.
Oh, good call on that. That's a mistake on my point. And that's a good reminder that I was thinking of this one. These are good things to review. I should have reviewed it myself. So good eye from the class. It should have been a 1 minus. That absolutely makes a humongous difference on these. I'm looking at secant inverse if I'm thinking in those terms. So go 1 minus x squared. Thanks again for spotting that one. Good eye. With that correction there, I think we're in good shape. Let's see what happens with this altogether. Again, I'm going to focus on the right side of the formula. Go uv minus the integral of v du, and then just drop in the quantities. U is cosine inverse. V is x, so we get cosine inverse times x. Usually we'll change the order and call it x cosine inverse, but it's fine as it is for now. Minus the integral of v. V is just x times du. Well, du is still a mess. That doesn't look too wonderful, but let's keep on going and see what happens. 1 minus x squared dx. That negative sign just looks funny. Let me fix that. So here's how we substitute it in. U is cosine inverse. And du is its derivative multiplied by dx. V is x. And so it goes in those slots as well. So it probably doesn't look great, right? We went from cosine inverse. Actually, that's a pretty complicated function. So I'd argue that this algebraic form here is slightly reduced in complexity. Now we have to solve this integral. And sometimes a good strategy here is, before you give up on it, see it all the way through. We can solve this one, even though it looks kind of messy altogether. It's not integration by parts a second time. Even though there's a function multiplied by another function, we can fix this one. We can rewrite this as cosine inverse x. I'm just copying the start times x. That negative can come outside, convert this to plus. We're now integrating x over the square root of 1 minus x squared dx. So that's our integral cleaned up a little bit more. Always a good idea to simplify your integrand as much as possible, because integration is not always straightforward. Anything you can do to simplify, cleaning it up algebraically is well worth that effort. And we can solve this one. Anyone happen to know the technique we need to use?
Trig substitution.
You know, that could work potentially, which would make it an unfair problem, right? That's a section 7.3 kind of problem altogether. But good eye, I think a trig substitution will work on this one. But again, that makes it slightly unfair. Cool thing about trig substitution is a good trig substitution problem sometimes has multiple ways it can be solved as well. So just because you're in section 7.3 on trigonometric substitution, we'll see some examples ourselves in that section, doesn't mean you have to use that method. Sometimes even that method could be simplified to something else. And the something else on this one is U substitution. But good eye. I believe trigonometric substitution does in fact work on that one. But since we're not there yet, we're going to hit it with a U sub instead. Let's go back to our review on day one. We've mentioned that part C here, that could have been done as a U substitution problem, but we absolutely didn't do it because the input is linear. This one's a better U substitution problem. It's kind of the prototypical one. And one way to spot them is you have a composition of functions. And the inner function, if you take the derivative, it appears as the function on the outside, something else in your problem. Now let's look at this one. That's a function composition, a square root composed with the quadratic 1 minus x squared. And the derivative of 1 minus x squared is a negative 2x. X appears, so that tells us U substitution is a great technique on this one. Grab the inner function, 1 minus x squared. That's going to be our U this time. Not the same as U and integration by parts. It's a new method, a new process entirely. I think of this U as being in a different scope as the original one. Purpose of this one is to solve that integral. It's 1 minus x squared. So that means when we go to do du, it's going to be equal to, this is a differential, so take the derivative of this, that's a negative 2x dx. We've got an x dx altogether. That tells us this will work. I'm going to divide out the negative 2 on this one, which is allowed because it's U substitution. We just can never do that in integration by parts. We have to leave that negative 2 exactly where it is when it's a by parts problem. So I'm going to rewrite this as negative 1/2 du equals x dx. So U substitution applies here. This all is the side work for making that U substitution happen. And now let's keep on carrying this down. On the next line, x cosine inverse x. I think that's a better format to write that. I forgot to put the x in front on that prior line. On this one here, we're not going to write in a plus. Well, it wouldn't hurt. Let's put it in just so we can see the substitution. But put in a little space after the plus. For x dx that's highlighted here, that all becomes negative 1/2 du. Negative 1/2 could come on the outside. Du goes here. All that's left then is 1 over the square root of 1 minus x squared, which we are calling literally u. And you know what? We can solve that integral. This is a section 5.3, 5.4 type of integral. 5.3 or 5.4 type of integral. So the original integral is nasty. It only could be done by section 7.1 methods that I'm familiar with. But then when we work through the process, we are reduced down to one final integral similar to what we've done in one of these sections. We can survive that last integration. We're well on our way. And it's not too bad to get through. Before we work our way through this last one, any questions with the process so far? Okay, in solving this one, what you'd want to do is a little bit of exponent surgery on it. If it's 1 over root u you're dealing with, it's just not convenient in that format with the power rule in reverse. So we write it as 1 over u power 1/2. We bring the base u to the numerator, so now exponent is negative 1/2. Now it's easier to get a clean antiderivative on that object there. So we rewrite this next as x cosine inverse of x. I'm copying up to this negative 1/2. And let's just write this in to show a paper trail in the notes of what we did here. U power negative 1/2 du. So now we're solving this one with the power rule in reverse. X cosine inverse of x minus 1/2. Then give it a little bit of space. Put the base u, add 2 over 2 to it. It's now power 1/2. We have to divide by 1/2 when we use that power rule. So we'll multiply by 2 over 1. And then add the constant c. So we've got the antiderivative of that piece there using section 5.3, 5.4 methods. Again, it's essentially the power rule worked in reverse. All that's left to do to finalize this problem is say what u is. So I think I can squeeze that in. One last step. We have that this is, let me push that problem down below. Finally, all said and done, it is x cosine inverse. This simplifies to just negative. You could keep the power as 1/2 if you prefer. If you want to convert it to a square root, it looks more fancy, but that's just a design choice, stylistic choice. U was 1 minus x squared, so we'll throw that in. Add the constant c of integration. So all said and done, that's where the problem lands. My claim is the antiderivative of cosine inverse is all of that. Kind of a mess, right? But, there's only one way to prove this. You have to differentiate that answer and get exactly cosine inverse. Any questions at all, folks, with getting through the main steps to land here? Okay, well, since it's week one, we've got about 10 minutes left. Instead of delving into a brand new problem, part D down below, we have a couple more to get through. Let's actually do the check on this one. Let's show how it goes. That's a good review in and of itself. Can you differentiate your answer and get cosine inverse x? That's a skill that we have to retain in Calculus 2, Calculus 3. So here's the check. It's not required. So if you skip the check, I'm not going to worry about that on homeworks or exams. But if you are taking, say, exam 1 or final exam, and you have a little bit of extra time, a check doesn't hurt. So here's what it would look like. We're taking all of that, differentiating it. So let me write that down so we know exactly what we're doing. X cosine inverse of x minus the square root of 1 minus x squared plus the constant c. Now, I'm noticing in that check, there's one nice little derivative that I like to take as a shorthand. If I differentiate with respect to, say, u or x, let's keep it as an x, the square root of x, you can take these same kind of steps and write root x as x to the power of 1/2. 1/2 would come down. The new exponent on x is negative 1/2, which means base x can go down to the denominator as a positive 1/2, which means it's just 1 over 2 root x. That's a pretty decent shorthand little formula for differentiating a square root, specifically a square root, because it saves a lot of steps, like writing down the exponent as 1/2, moving it down, moving the base around like we did here. So I'm going to use that formula in my check just to make sure it's not too many lines. Okay, so here's the next portion of the check. On that very first term, it's a product rule computation. Oh, I forgot the prime. Don't forget in the check, you're differentiating. That's a weird omission to make. So when we said integral here, it was an antiderivative. So we better be able to differentiate that and get the integrand back. So product rule, I'll differentiate that x first. It'll turn into a 1. Copy cosine inverse x. Then we take x, copy it, multiply it by the derivative of cosine inverse x. Minding the error above, make sure it goes root 1 minus x squared. So this will be negative 1 root 1 minus x squared. So that's the derivative of cosine inverse. Then here, we'll copy the negative sign through the constant multiple rule. Differentiate the square root. Through the shortcut above, here's how the square root always gets conveyed. It's going to be 1 over 2 times the root of something. So if it's 1 minus x squared inside the root, that's the thing that goes down below. But now it becomes a bona fide chain rule. We chain on the new derivative of 1 minus x squared. So that's going to be times negative 2x. The derivative of the arbitrary constant, because it's a bona fide constant, goes to 0, so that's gone. So we're left with a good amount of mess, right? But the closer you look at this, this is not too bad. This is altogether negative x over the root of 1 minus x squared. Here, the 2's cancel, the negatives cancel. That's positive x over the root of 1 minus x squared. Let's write it in just to emphasize. Cosine inverse x minus x over root 1 minus x squared plus x over root 1 minus x squared is what you get when you cancel out everything here, negative signs and the 2 and the half. But then the roots cancel off. You really, honestly, and truly get cosine inverse of x. It's not a miracle. It was just careful work with integration by parts and a tacked on u substitution. Calculus has a way, just like much of mathematics, of just building on top of itself. When you took a Calculus 1 class, you probably noticed that logarithms, trigonometry, factoring, exponent laws, they don't go away. They suddenly become emphasized massively on many, many different problems. In a Calculus 2, it's the same story. We have to recall our derivatives, watch out for weird errors like these. Any prior method, like U substitution, it tacks on to our next techniques. So U substitution doesn't live in isolation. It goes along with integration by parts. This would be a pretty decent homework problem in its own right. But as in terms of exam problems, I tried to make the exam problems a little bit more reasonable. This feels like 2 problems worth in an exam setting. So I'm not going to write super long exam problems like these, but this is an important skill to get through them. We will practice them in the homework. So that's why we're supporting them in the notes as well. So that's what the check looks like. Any questions at all, folks, on the derivative side or the antiderivative side? Okay, well, integration by parts. This one is a particularly tricky one because U substitution showed up out of the blue. Sometimes integration by parts is tricky because you have to use it twice. It's kind of similar to the last one. It's 2 problems duct taped together in a certain sense. Other times integration by parts is really just this, run through the method. That would look like a pretty decent exam problem right there. Plenty of homework problems look like that. And when we come back on Thursday's class, that's where we're going to pick up. This one looks awful, but really it's not too bad. We'll do a couple more, practicing the same techniques, but as definite integrals, we have to give the definite integrals some attention. Then we're going to jump into trigonometric integrals. Really, at its heart, all 7.2 is a whole bunch of U substitution. So we're going to practice that a lot here. The thing that makes this kind of tricky, a bona fide Calculus 2 topic is, it's going to use a lot of your skills from trigonometry. Trigonometric identities, the Pythagorean laws are going to be major here. Simplifying trigonometric expressions will be used. So if you feel a little bit rusty on trigonometry, this is a good set of notes to review over here. But because these problems, as you saw, kind of get a little bit long, I'm going to try never in this semester start a problem we have to finish on the next class meeting to the best of my ability. So I'd say this is a pretty good stopping point for us. Any last questions or thoughts at all, folks, before we call it a night? Okay, well, we're getting through it, folks. We're kind of opening up section 7.1 a little bit slow, emphasizing the review side as we go, just so that we can get lots of refreshers from Calculus 1. But as we get through this section, 7.2 is going to be a little bit slower, or excuse me, a little bit faster. 7.3, a little bit slower again because it just has more trigonometry going on. Usually we're going to take anywhere between 1 and 2.5 days to complete a section, just depending on how much variety there is in problems, how much complexity there is in the sections. But we'll be finishing this one off next class meeting, starting off the next section. Have a great night, folks. We'll be back to it on Thursday. So we have kind of a catch-up period on Wednesday, take a break, and then back to it. That'll be our pattern for the rest of the semester. Thanks. Have a good one. Yep. Take care.